Okay, guys, good afternoon. Welcome to class. Let's go ahead and get started. Now, before we begin, I just want to let you guys know that I've been at a conference all week. My flight back to Singapore was very delayed. I didn't get home till 4 a.m. this morning. If I appear a little bit tired and sleep deprived in today's lecture, I apologize. I very much am. So with that caveat in mind, let's go ahead and get started. Okay. We have another Stats Matters activity. This semester, I've been asking you guys to think about how statistics and research methods is relevant not to just passing this class, but to many different areas of your life. So you guys have talked about how it's relevant to perhaps your other classes, and now I'm giving you guys to think about how it's relevant in your daily life. So I want you guys to think about any kind of media that you've come across. This could be like a podcast, a TikTok post, a newspaper article, whatever it is, something that you watched on TV, whatever it might be. And if it inspires you guys to think about something related to research methods and statistics, things that are related to this class, then write about that. Write about how it's related and what this makes you think about. You can submit this for one extra bonus point on your final exam on Canvas. Okay, so let's go ahead and start with today's content. We are going to talk about different ways of building your linear regression model. So we're going to build up on what we talked about last week, and then we'll talk about how we can use these different methods of building your linear regression model to investigate things like mediation and moderation. Okay, so let's go ahead and start off with a root clap. Does the order in which you add variables to your regression model matter? Go ahead and vote, yes or no. Okay, so does the order in which you add your variables make a difference? Does it matter? So it's pretty split, actually. So this is what we're going to be talking about today. How does the order in which you add your variables, the way in which you add your variables, affect the model? It does. And that's one of the things that we're going to show is that how you add variables to the model will affect how you can interpret the results. Now, guys, overall, if you add all of the same variables to the model in any order, the end model is going to be the same. But your interpretation of the importance of the variables and what each of the variables are doing to the model might change based on the order in which you add your variables. And there are reasons why we might add variables in different orders. So that's really what we're talking about. Okay, so this lecture today is building on linear regression. Now let's just do a really, really brief recap from last week, because linear regression is going to form the basis for what we talk about not only today, but also for the subsequent weeks when we start going into ANOVA. Because all of these, the correlation, linear regression, ANOVA, they're all based on the same underlying structure of a general linear model. So you guys recall that we had that line of best fit that describes the data in our data set. And this was defined using that equation y is equal, or the predicted value of y is equal to b0 plus b1x1 plus some amount of error we can't quantify. Now that b0 refers to the y-intercept. That is the predicted value of y when all of our predictors are set to 0, right? And then we can look at the change in the y-score for every 1 unit increase in our predictor, and that's defined by that B1 coefficient. So that defines the relationship between our predictor and the outcome variable. So we might have a positive coefficient, which would mean that increases in our predictor are related to an increase in the y-score. We could also have a negative coefficient, which means that an increase in our predictor is related to a decrease in the y-score. And that slope tells you how that predictor is related to the outcome variable, right? So if we have a very steep slope, that suggests that bigger changes in y are observed for every 1 unit increase in x, compared to if the slope is really flat and horizontal, right? And in fact, if it's not even different from 0, if it doesn't differ significantly from horizontal, from flat, then we would say that the change in the predictor, in fact, doesn't even have a reliable effect on the outcome variable. So we use the linear regression to help us predict the outcome of y. And this helps us improve our prediction accuracy compared to if we were to just use that mean of the y scores, what we might think of as called like a basic model, right? So if I was trying to guess your exam score, I could look back at the previous years, look at the average exam score and say, yep, this is what I predict you're going to get. Not a bad guess, but if I know that there is a relationship between how many hours you spend studying each week and your exam score, I can improve my prediction accuracy of your exam score by knowing how many hours you studied. So if you studied just a little bit, I might think that you're going to get actually maybe lower than the average. And if you studied a lot, I might think maybe you're going to have a higher score, maybe even higher than the average. So we're going to use the relationship that exists between our predictor and the outcome variable, or predictors and the outcome variable, because of course we can have multiple predictors, to help us improve our prediction accuracy. And the more predictors we add to our model, the more we can eat away at that unexplained variance. So the more variance we can explain. And you recall that when we are doing linear regression, ultimately we are comparing the variance that we can explain in our model relative to the variance we cannot explain. So the variance that we can account for because of the predictors and the relationship between the predictors and the outcome variable, that is that sums of squares regression, which we will then transform into a mean squares regression, or mean squares model. This is the variance we can explain using our regression model. And we're going to compare this to the variance we cannot explain, which is quantified by that sums of squares residual. So that's the variance due to all the other stuff that we're not including in our model, like individual differences, various other variables that we just haven't included, right? And we compare this using that F ratio, and if we get a statistically significant F ratio, this suggests that our model is explaining a reliable amount of variance, and we should be using it. It does help us improve our prediction accuracy relative to just using that basic model alone. All right, any questions so far? Good, because that was just a recap from last week, so very good. Okay, now when we did this last week, what I was showing you was just putting all of these variables in. We started off with a simple linear regression with just one predictor. And then we added a little bit of complexity by adding multiple predictors. But the overall story was the same, right? We're still looking at the overall explanatory value of the model. And then we talked about how we can break down the contribution of each one of the predictors by holding all other predictors constant. And we do this looking at those t-tests, right? So when we look at the coefficients table, we can evaluate to what extent are each predictor contributing to the overall explanatory value of our model. Because, as we discussed last week, maybe you have like a group project where you have 3 out of the 4 people are doing all the work, one person's getting credit, but they haven't actually contributed to the project at all. And likewise, we might have a multiple regression model where 3 out of our 4 predictors are really helping us improve our prediction accuracy, but one predictor has not related to the outcome variable at all, but is still getting credit in the overall model. But when we look at the coefficient table, we can start to see which of the predictors is really helping us improve our prediction accuracy. Which of those predictors has a slope that differs significantly from 0 when we hold all of the other predictors constant. And of course, if we have a categorical variable, we're always comparing this to our control level that we didn't include. So relative to first year students, relative to males, this is the effect of being a female. Relative to being a non-psychology major, this is the effect of being a psychology major, right? So it's always relative to whatever you have put as your 0 or your control category. Okay, now when we build regression models, we don't want to just throw in every single variable under the sun. That's not good practice. When you do any kind of experiment or any kind of research study, you don't want to just add as many variables as possible. You do want to be a bit thoughtful and mindful about which variables to add to your research study. Because the more variables you add to your design, the more power you need in order to get a significant effect, right? It's going to reduce your degrees of freedom. And so you're going to have to increase the sample size by a lot when you start adding more variables to the model. Now, of course, we don't want to limit ourselves. If we have variables that we think are relevant, that we think are going to really help us improve the prediction accuracy, then yeah, add them. But be thoughtful about which variables you add. Don't just add any variable. Have a reason for adding these variables. We want to maximize the R squared. You guys remember that the R squared is the proportion of the overall variance that our model can explain. It's basically the effect size. It tells you how good is your model in terms of it can explain 34% of the variance, or it can explain only 5% of the variance, or whatever it might be. So it's telling you of the overall variance in the data, how much of this can your model explain. And we want to explain, obviously, as much variance as we can, but using as few predictors as possible. Okay? So we want to go for maximum efficiency. Choose the predictors that are going to give you the most bang for your buck. And this comes from, one, just knowing the variables you're working with. So a good literature review is going to help you identify which variables you should add to your model. Right? This is why, one of the reasons why we do literature reviews and why you shouldn't just kind of quickly skim through and just find what you need just to write up your introduction and call it good, right? No, you want to spend time really understanding the variables that you're working with, the theories that relate how, or that explain how these variables are related together. Because that's going to be the first step in helping you to identify which variables you should add to your model. So include variables in your model that are going to be what you think helpful or interesting. And there are 3 ways that you can add variables into your model. The first is simultaneous. This is what we did last week. Throw them all in, right? Chuck all the variables in together, push go, and just see what the final outcome is. That's what we did last week. So that is sometimes referred to as an enter method. And then there are 2 sequential ways of adding variables to your model. We'll go through each of those. One is hierarchical. This is a theory-driven approach where you, the researcher, decide the order in which you're going to add the variables to your model. Or you can do a statistical approach, which uses the data to determine which variables are added to the model and in which order. All right, so last week, we had this example where we're trying to predict your exam score based on a set of predictors, and we're using the number of hours you studied, whether you're a psychology major, and what year of study are you. And we built a regression model last week to predict your exam score, and we included a coefficient for every one of our predictors. And you recall that when we have a categorical variable, we also had to dummy code that, right? So we're looking at the effect of each of these variables on the exam score. And last week, we threw them all into the model, and we pressed go. We left out the first years because that was our control level, and we left out the non-psychology majors because that was also our control, but otherwise we just said go. And we got a final result. I believe that only hours studied was the only significant predictor. I can't remember if psychology major was or not. But basically, we got a nice final model at the end that told us, yes, our model does seem to improve our prediction accuracy, but not all the predictors are helpful. Okay, so let's not spend too much more time on that one. Let's go and start talking about how we can add variables to our model sequentially. And the first one is the hierarchical method. And this is the one that is theory-driven. This is where you decide the order to add variables because you are trying to assess the relative importance or the relative validity of 1 or 2 particular variables. So you have a whole bunch of variables, and we always include variables that we know are relevant but aren't of usually theoretical importance. A lot of demographic variables, right? We know that your age, your education, your income, these are things that tend to affect everything. Most of the time we're not that interested, but we know that they can explain a lot of variance in and of themselves. From whatever question it is you're looking at, whether it is grades on an exam, whether it is somebody's aggression score or their depression score, whether it is, I don't know, your happiness, whatever it might be, we know that these things tend to be affected a lot by your age, your gender, your income, those kinds of demographics. We don't want to ignore that. We know that these things have a lot of explanatory value, but that's usually not really what we're interested in. We're interested in something above and beyond that. We're maybe interested in the effect of the strength of your social network, or maybe we're interested in, how your, the quality of the school that you went to, or whatever it might be. So we have a bunch of variables that we know are related to the outcome variable that we need to put in the model, but then we want to assess how much value, predictive value, does the strength of your social network have on finding joy in your free time, or what was it, overall happiness, I think, well-being, right? Once we've accounted for the variance that can be explained by these other demographic variables. So once we explain the variance due to all this other stuff, does your strength of your social network improve the prediction accuracy above and beyond those we've already included in the model? That's what we're doing with the hierarchical model here. So we're going to assess whether there is a significant improvement or increase in the R squared, which is the proportion of variance explained. So whether there's a significant improvement in the explanatory value of our model when we add the variables of interest. Right? So we account for the variables that we're not that interested in. Those are what we call maybe the control variables, or just your demographics, whatever it is. And then we start to add variables that we're actually interested in. Do these result in a significant improvement in the explanatory value of your model? And we add each of these one by one to see what is the change in the model as we add variables to it, one at a time. Do we see a significant improvement in the model? Okay. So begin with the control variables in your first block. Whatever it is that you're not that interested in, but you know are important and you know have some explanatory value. Because it's possible that maybe the strength of your social network doesn't have any additional explanatory value once you've included the variance explained by these control variables. So maybe strength of your social network doesn't add anything beyond that. And this is what we're going to test here. So add the control variables into the first, and then add variables of interest into your model one at a time. If you have any categorical variables that you've dummy coded, those will need to be added all at the same time. So what we're going to do is basically build multiple regression models, and we're going to assess the explanatory value as we add variables one at a time. So we're going to start off, maybe we look at whether you're a psychology major, then we're going to start add in the psychology major plus what year level are you, and then we're going to look at whether there's a further improvement in the explanatory value of the model when we look at how many hours you studied. So this allows us to assess each one of these one at a time. Now I said add these into the first block, subsequent blocks, whatever. And this is using the terminology of SPSS. So you can see here that when we add variables into model, it says block 101. And last week, we just chucked everything into the first block, and we didn't even look at this. But you could have pushed next, and then this gives you another block. This is going to create another model. Now, it includes everything you had in the first block, plus whatever you're adding now into the second block. And then again, we can add another block where we put in our third variable of interest. And this block is going to include everything from the first block and the second block, and now what you've added to the third block. So we can start to build a model by adding variables one at a time to assess what does a model look like when we have different variables in it. Again, if you have any dummy variables, do make sure that you add all of those into the same block. Okay. Now, the things you need to ask SPSS to give you are mostly the same, but do ask for the change statistics. So importantly, there's an R squared change. Again, your R squared is the proportion of variance explained. It's the effect size. It tells you how, basically how much value, explanatory value your model has. And we can assess whether there is a significant improvement in that proportion of variance explained when we add variables to our model one block at a time, or one step at a time. Okay, any questions so far? Okay, so you're going to start off by getting some overviews of the data. This is not going to look any different from what you did if the variables you added are all the same as if you did simultaneous versus this hierarchical method. These first few tables are going to be exactly the same if the variables are the same. But then you're going to get a table here that says the variables that have been entered or removed. Now last week, it just had all the variables here. We just kind of skipped through that. But here, what it's showing you is that there are 3 models being assessed, and each model has different variables in it. So the first model has only psi major. That's the only variable that was entered. The second model, if you look at the bottom, it says dependent variable. So the second model is going to include, yes, the psi major, but it's also going to include the year levels. So that's the variable has been added, or all the different year levels. And then the third model, we added hours studied. So this is telling you each of the variables that were added to your model so you understand what each model is testing. So this is telling us that we have 3 models. And throughout the rest of the output, you're going to see output for 3 models. So now we can assess the change in the model as we add predictors to it. So again, look at the notes underneath. It tells you that the first model includes the constant, which is that y-intercept, plus psi major. The second model includes the constant, the psi major, plus the year levels. And the third model includes the constant, psi major, year levels, plus hours studied. So this is telling you that each subsequent model includes the previous variables as well. So you're just building onto it. You're not removing anything at this point. So if we look at the final model, that third model, this is going to be exactly like what you got last week because the variables we've added are exactly the same. If that's all you're interested in, is just that final model with all the variables, then there's honestly no need to go through multiple steps. You just do what we did last week. The point of doing this is to assess the change in the model when you've added the variables one at a time. Okay, so just kind of keep in mind why you're doing this. We're assessing whether there is a improvement in the prediction accuracy of our model, whether the proportion of variance explained has a significant increase when we add our study to the model. So it goes from 0.052 to 0.074. That is, if you the r squared going from model 1 to model 2, if you look to the, here. If we look at the r squared, for model 1 is 0.052, so this only explains, with psi major, it only explains 5.2% of the variance. Once we add the year levels, now it's 0.074, so we can explain only 7.4. That's only an improvement of 2.2%. That's pretty small. But when we add hours studied, it goes now to 0.45. So now, with all 3 of these variables, we can explain 40.5% of the variance. And that's a change in the explanatory value of 0.330. So that's pretty big. So this is telling us that, hey, there's not a really big improvement in the prediction accuracy of our model just by adding the year levels, but there's a big improvement when we add hours studied. And F change, we see is it goes from 5.3 to 0.76 and then now 52. So there is a significant change in the F when we go from model 2 to model 3, but not from model 1 to model 2. So there is not a significant improvement in the model when we just add year levels, but there is a significant improvement in the model when we add hours studied. So these R squares and the change, so the R squared change and the F change, these can be really useful for understanding the incremental value of each of your predictors when you add them to the model. The rest of the tables are going to be the same. All you're going to see is how the model changes as you add each predictor. But the information in terms of it's telling you the sums of squares model, the sums of squares residual, that mean squares, the degrees of freedom, the F, that's the same information that you got last week. It's just now you get it broken down for each one of the models. So you can see how it changes as you add predictors to your model. And the same is true for your coefficients. So if we look at model 1, that only includes the psi major. It has a coefficient of 8.251, and this is a significant predictor. So a change in the psi major, so relative to non-psychology majors, being a psychology major does have a significant improvement in the exam score. So now we're going to add year levels to see what is the impact of year levels. And this might have an impact on earlier ones, right? Because now these variables we're adding to the model start to also explain some of the variance that the previous variables explained. So psi major is still a significant predictor, but our year levels are not. So these variables are not going to improve the prediction accuracy. A change going from year 1 to year 2, or year 1 to year 3, or year 1 to year 4, none of these seems to have an effect on the exam grade, because these slopes are not significantly statistically significant. Again, this is the same information that we got last week in terms of the coefficients table. It's just now giving it to you for each step of your model. Our final model is model 3. This includes the psi major, year levels, and the hours studied. So let's look over here. We have the psi major, which was earlier a significant predictor, is now just doesn't quite meet the cutoff anymore. Why? Because the variance that was explained by psi major, some of it is now being explained by your hour studied. So it's no longer that being a psychology major or a non-psychology major seems to have a significant impact on the grades, but the number of hours you studied does. So this tells us that the number of hours studied has a significant improvement in the model, that this does have improved our prediction accuracy, and that this, in fact, explains some of the variance that was earlier explained by the psi major variable. So if you're doing this as a research project and you're wondering what is the impact of the number of hours studied, does this improve the exam grade above and beyond that, which can be explained by your major or what year level you are, you would say, yeah, it does. There is a significant improvement in the prediction accuracy of our model by adding hours studied to the model. And the psi major, the hours studied does have a significant impact, that for every 1 unit increase in hours studied, the grade should increase by 4.434. And none of the other predictors are a significant predictor of grades once we've added hours studied into the model. So you can see how this changes your interpretation of how each of these variables are related to the outcome variable by doing this sequentially. Okay, any questions so far? Now, finally, you're going to see a table that says variables entered or removed. Excluded variables. The excluded variables should correspond with the first table you saw, variables entered and removed. So the first variables entered and removed, we had the first model where we only included psi major. That means we excluded all of the other variables, and that indeed is what it's showing here. So the first model, we excluded your year levels and the hours studied. The second model, we added year levels, and previously we also added psi major. So that means in the second model, we excluded hours studied. And there's no third one here because we included all the models by the time the third model came around. Okay, so that's the hierarchical method. This is a way of assessing the incremental validity of predictors, and the reason you would do this is to assess whether a certain predictor or predictors improves the prediction accuracy of your model above and beyond variables that you control for. Okay? Now, the other way that you can add variables to your model is using a data-driven method, sometimes called the sequential method, although I don't really like calling that because there are variations of this method, this data-driven method. So you can have a forward, you can have a backwards, and you can have what's called a stepwise method. And each of these refers to how the variables are added to the model. Forward means we add variables one at a time. Backwards means we chuck all the variables into the model and then we remove them one at a time. Stepwise is a combination of the forward and the backward criterion. Generally, we don't recommend using the stepwise method because this can result in overfitting of the model to the data, which means it lacks generality. It lacks that external validity. So we usually will do either a forward method or a backwards method. So either we add variables one at a time or we remove the variables one at a time. So the way in which the variables are added or removed is based on the semi-partial correlations. So again, remember that the hierarchical method is theory-driven. You decide the order to add variables based on some theory that you're testing. I have theorized that the hour studied is a really important predictor, and therefore I'm going to put this into my model last to assess the increment of validity. But when we do a forward or backwards method, we're letting the data decide the order. So whichever variable has the highest semi-partial correlation, that might get added first. And then the variable with the next highest semi-partial correlation, that gets added next. So the variables are added based on the relationship with the outcome variable, and so you don't control that anymore. And note that not all variables might be added, because if variables do not have a significant semi-partial correlation, then they just don't get added at all. Now you can determine, you can change the likelihood of a variable being added or removed if you wanted to. I generally don't recommend modifying these, but you can play around in your tutorials just to see how this would influence the process. Again, if you do this method, forward, backwards, stepwise, it doesn't matter. The first couple of tables are going to be exactly the same because this is just describing the overall data. So it's still going to be the same descriptive statistics and the same correlations, assuming that you've added the same variables to the models. Now, I've done a forward method here, and the reason I know this, and the reason you would know this, is because it tells me method forward. Using the criterion, probability of F to enter is less than or equal to 0.05. If I had done it backwards, it would say backwards here. So this is telling you how these variables were entered. What was the methodology? And it tells me again which variables got entered. Now I only have one model here. I put all the variables in. I put all my variables into this, and I said, give me a forward model. But in the end, I only get one model with one variable. Why? Yes, but why do I only have one? So I have like I have several variables. So this should add variables one at a time based on the semi-partial correlations. So why do I still only have one model with one variable? Thank you. Yeah, because there's only one significant predictor that has a significant, or one predictor has a significant semi-partial correlation. Then I only get one model. So if I had multiple predictors with significant semi-partial correlations, then I would have multiple steps. I would have maybe 2 models, 3 models, 4 models, right? But because I only have one variable with a significant semi-partial correlation, I only get one model in the end. So again, this is letting the data decide the output. So in the previous model, the hierarchical version, I decided which variables to add. And I ended up having variables that were not significantly related to my outcome variable. The year levels were not significantly related. And in fact, neither was your major once I've added all the variables to it. So this kind of cuts through that, and it's only going to add the variables that are significantly impactful. Anything that isn't just gets excluded. They never get included at all. Okay? So, in the end, I get a output that has only one model. Now again, if I had multiple predictors with a significant semi-partial correlation, then I would see multiple models for each one of my tables, just like what we saw for the hierarchical version. It's just that we only in this case have one. But again, the whole idea is that we can see the increment of validity as we add variables one at a time based on those semi-partial correlations. Here's the backwards. So we put all the variables in, we say backwards. This is the variables that have been entered, and then we've removed these variables one at a time. And so then we get 4 models here because we are removing them one at a time. Okay. So that's it. Now, you can also do a combination of this. So you can have, for example, an enter or like a forward method at the beginning in block 1. And then you can add another variable, the variable of interest in a block 2, for example. So you can kind of mix and match these different methods here. Okay, so build your model by adding variables, and you can add all the variables simultaneously or sequentially. Now, sequential methods will vary based on whether the researcher retains control of the order and which variables are going to be added to the model. Or you can use a more data-driven approach, which is based on the semi-partial correlation between each variable and the outcome variable. Any questions? Okay, so let's move on. Now, the reason we're talking about this is because we use the sequential method for helping us to assess things like mediation and moderation. So, hierarchical models are used for mediation and moderation. What is mediation? Well, this is something we talked about in week 1. Mediation is when a third variable is involved in the correlation between a predictor and the outcome variable. It is part of what we say is the causal chain. So the predictor does cause a change in the outcome variable, but it's because of the mediator, right? So maybe, yeah, finding more free time and finding more joy in your free time does cause a change in your overall well-being, but it's because finding joy in your free time results in a improvement in physical health, which then leads to an improvement in your overall well-being, maybe. So when we talk about mediation, we're talking about a variable that is part of the causal chain of events. So again, yeah, joy to life satisfaction. Joy leads to lower blood pressure. Lower blood pressure leads to more life satisfaction. Hours studied is related to grades. Maybe we see that hours studied leads to more interest in your statistics, and it's improvement in interest in statistics that leads to better grades. So when we talk about mediation, we're talking about a causal relationship, but it's being mediated, or it's through another variable or variables. Now, we can have mediation with multiple mediators. we are going to keep it simple. We're going to talk about mediation with a single mediator variable, but do be aware that we can have multiple mediators. We might have our study leads to improvements or increases in interest in statistics, which leads to increases in, I don't know, attending more classes, which leads to increases in grades, right? So you could have multiple mediators in this chain of events. Okay, now we are a little bit short on time, so I'm not going to spend time on this, but I want you guys to be thinking of other examples of statistical mediation and how you might use this, because in fact, mediation is a really, really common statistical technique. You see this everywhere in the literature. Okay, mediation assumes a third variable as part of that causal chain between variables x and y. It is what links those variables together. Okay. So let's talk about how we might assess mediation. Does mediation occur? All right. A mediator is a variable that presumably is linking the predictor and the criterion variable. So if we were to control for this mediator, we can look at the relation between our predictor and the outcome variable independent of our mediator variable. So if we hold constant the variance due to the mediator, is there an improvement in the explanatory value of the model once we have added our predictor to it? This hopefully sounds a little bit like what hierarchical regression is doing, because that's exactly what we're going to do. We're going to use hierarchical regression to assess mediation. When we hold constant, or when we account for the variance explained by our mediator, does adding our predictor have a significant improvement on the prediction accuracy of the model above and beyond that which was already explained by our control variable, or in this case, our mediator variable? So, can we still observe a significant relationship between the predictor and the outcome variable once we've controlled for the variance that was explained by our mediator variable? That's the question. Now, in mediation, there is some terminology that you guys need to know. This is just kind of set terminology that you always see. The relationship between your predictor and the outcome variable is referred to as link C. And this is the zero order correlation between x and y. So if we were to just chuck those into like SPSS and say, give me a correlation, it's going to result in a standard Pearson correlation. This is what we call the zero order correlation. It's not accounting for anything else. It's just the correlation between variable x and variable y. Okay, so this is what we refer to as link C, and we can predict what y will be as a function of x by looking at the y is equal to b0 plus b1 hour studied. So that's your standard regression model here. We also have paths A and paths B. So path A is the relationship between hours studied, your predictor variable, and the presumed mediator variable. So this is always referred to as pathway A. Pathway B is the relationship between your presumed mediator and the outcome variable. So pathway C is the zero order correlation between your predictor and the outcome variable. That's the one that we're really interested in. Path A is between the predictor and the mediator. Path B is between the mediator and the outcome variable. Okay? Now, each of these is essentially a correlation. We can predict whatever it is we're trying to predict. So we can predict the interest in statistics as a function of hours studied. We can try to predict your grade as a function of your interest in statistics. Right? So if we look at all these together, we've got hours studied is related to the grade, but hours studied also has a relationship with our presumed mediator, and the mediator has a relationship with our grade. if we want to predict what is your grade as a function of both hours studied and the mediator, we're going to do a multiple linear regression where we include hours studied and interest in statistics as predictors. So we can look at the effect of hours studied on grade and the effect of interest in statistics on the grade. So our final regression model will include both our predictor and our mediator as predictors. Everyone's with me so far? All right, now I mentioned that path C is the zero order correlation between your predictor and the outcome variable, y. C prime is the relationship we get when we have controlled for the variance due to the mediator. It's the partial correlation. So C prime is the relationship between x and y once we have controlled for this link here. So C is the total effect. C is when we don't control for anything. This is the relationship between x and y without thinking about the mediator whatsoever. C prime is the mediated direct effect. C prime is the relationship between x and y after controlling for your mediator. In other words, after removing the variance explained by the mediator. So it's the total effect minus the paths A and B. C prime is the relationship that you have between your predictor and the outcome variable once you remove the variance that has been explained by the mediator variable. Think back to the hierarchical method we just discussed. When we add variables to the model, we're assessing the incremental validity of that variable above and beyond that which was already explained by the previous variables. So once we have already explained the relationship, the variance due to interest in statistics, is there a significant improvement in the prediction accuracy when we add hours studied? Does this have a relationship between, is there a relationship between hours studied and grades that is more than what we can explain just from using interest in statistics? Okay. Now the indirect effect is the strengths of paths A and B. It's literally just the mediation effect. So do we have a significant mediation effect? That would be indicated by these two paths here. Okay, any questions so far? So you're talking about like this one here, I mean? Yeah. So the total effect is just all these things added together. So it's just mathematically that's how it works. But the indirect effect is looking at the strengths combined. So it's the product of those. It's always going to be the product of A and B. You don't add them. It is always just the product of those things because it's not just the sum of them. It's just the way it is. Yeah. But this total effect is always going to be the sum of all these links together, of all the pathways. So the total effect is when you look at all the ways in which X can lead to Y, you just add them all together. The mediated effect is the relation between X and Y, removing the indirect pathway. Okay, so if we go back here, if we look at the relation between our predictor and our criterion variable, and we look at the combination of all three of these pathways, that's your total effect. Once we explained the relationship or the variance due to the mediator, whatever's left over is the path C prime. Maybe there's something significant left over, maybe there's not. That's the question. So how can we do this using the hierarchical method? We're going to add the variables one at a time to assess the incremental value of our predictor and see if it has any improvement in the model's prediction accuracy above and beyond that, which is already explained by the mediator. Now, first, we need to establish that the mediator actually is a mediator. Does our predictor significantly predict the mediator? And does the mediator significantly predict the outcome variable? Because if it doesn't, if X doesn't predict M, or if M doesn't predict Y, then it can't be a mediator, right? If there's no relationship between the number of hours you studied and your interest in statistics, then there's no way that interest in statistics can mediate the relationship between hours studied and grades. Likewise, if interest in statistics doesn't predict hours studied, again, it can't be a mediator. So we need to first establish that our predictor does have a significant relationship with our mediator, that it can predict the mediator, and that the mediator can predict the outcome variable. So we need to establish those A and B pathways. Then we need to assess whether or not there is any improvement in the prediction accuracy of our model when we add our predictor to it after controlling for the variance that can already be explained by our mediator. All right, this can be quite tricky. So if you have any questions about the logic of this, please speak up now. Any questions? Okay, I'm going to take the deafening silence as a cue to go on. So we are going to first assess whether or not we can get a path A. Is there a significant relationship between our predictor and the mediator? So X should predict changes in Y. Okay, we'll start first here, I guess. Do we have a significant relationship between X and Y? Does hours studied significantly predict changes in your grade? So we're going to do a simple linear regression. We're going to add so we're going to look at grades as a function of hours studied. And then we get an R, right, 0.614, so this can explain 61.4% of the variance, not bad. And this is significant. So yes, there is a significant relationship between hours studied and grade. So that pathway C is established. Great. So this gives us an unstandardized coefficient of 4.608. That's what pathway C is. So the relationship between hours studied and grade without controlling for anything else. Next, does our predictor predict the mediator variable? That's the pathway A. So we're going to predict ratings of importance or relevance of statistics. That's what we think is the mediator. Improvements in grade lead to improvements in how important you think statistics are. Sorry, improvements in hour study leads to improvements in how important you think statistics are, which leads to improvements in grades. That's what we think is happening. So we're going to try to predict importance or relevance of statistics ratings as a function of our predictor, hour studied. So we get a R of 0.714, and this is significant. This gives us an unstandardized coefficient of 0.817. So if we look over at our model, pathway A is 0.817, and this is significant. So yes, there is a significant relationship between the number of hours you studied and your ratings of how important or how relevant you think statistics are. Next, our mediator should predict changes in our outcome variable. If it's a mediator, then this should be significant as well. So again, let's take a look over here. We're trying to predict the grade as a function of ratings of importance or relevance of statistics. This model can explain 0.854 of the variance in grades, and it is also significant. And we have an unstandardized coefficient of 5.596, so we would put that over here. So each one of our paths are statistically significant. So we know that the relevance of, or ratings of relevance or importance of statistics does seem to be related to or can explain variance in grades. Now, is this mediating the relationship between hours studied and grades? That's what we're going to assess in step 4, our final step. Here's where that hierarchical regression model comes in. We are going to assess whether or not there is an effect of hours studied on grades once we have controlled for the variance that was already explained by our mediator variable. So we're going to do this in 2 steps. We're going to add our presumed mediator into step 1 to assess the effect of stats ratings on grades. We're going to see how much variance can be explained by our mediator. Then in step 2, we are going to add hours studied to see whether our study can explain any variance in grades above and beyond that which was already explained by our mediator variable. So we're going to look at the incremental validity of hours studied. Okay, any questions so far? So we're going to do this as a hierarchical model. We're adding our variable of interest into the second block to see, does it improve the prediction accuracy above and beyond that of explained by our mediator? So here we can look at that C prime pathway. So we're trying to predict grades, and we've got 2 models. The first model is just our mediator. And in the second model, we add our variable of interest, our predictor. Here's what we get. First model can explain 0.854, has an R of 0.854, R squares, none of these seem to change at all. So not much improvement here. And in fact, going from model 1 to model 2, there is not a significant change in F. So already we can see that maybe there is not additional variance explained by our predictor once we explain the variance that's accounted for by our mediator. And in fact, that's exactly what we see. So in model 1, with just our mediator in the model, there is a significant relationship between ratings of relevance and importance on grades. So for every 1 unit increase in these ratings, we see that the grades are likely to improve by 5.596. Now, when we add hours studied into the model, there is not a significant effect. The slope for hours studied does not differ significantly from 0, which tells us that even though path C was significant, there was a significant relationship between hours studied and grades. When we remove the variance that can be explained by the mediator, this path is no longer significant. That's what it's telling us. So it tells us that, yes, mediation was occurring. There was in fact, what we might say is full mediation. The variance between how hours studied was related to grades can be completely explained by interest in statistics. Hours studied doesn't have any explanatory value or any explanatory predictive value on grades above and beyond that which was already explained by interest ratings and statistics. So this is telling us that when we account for the relationship between interest and statistics and grades, there is no longer a significant relationship between hours studied and grades. That relationship was fully mediated by the interest in statistics. So the reason hours studied leads to improvements in grades is because hours studied changes your interest in statistics, and interest in statistics changes grades. That's what this is telling us. Now, when you have a significant total effect and a non-significant mediated effect, we call this full mediation. The relationship between X and Y was completely mediated by your third variable. It was completely explained by your mediator. If we had a situation where there was still a significant mediated effect, but just weaker, we would call this a partial mediation, which means that the hours studied does have some explanatory value above and beyond that which was already explained by the number of hours, by the interest in statistics. That some of the variance between hours studied and grades was accounted for by interest in statistics, but some of the variance was not. There is still a significant amount of variance that can be attributed to just hours studied alone. That's an example of partial mediation. All right, any questions so far? Yes. Yeah, you're still looking at the less than 0.05. So these are holding all of the variables constant. So just like what we did last week, where we're assessing whether the slope for each of these variables differs significantly from 0, we're looking at the t-test. So the t-test is assessing whether the slope for that predictor is significantly different from 0 while holding all of the other variables constant. So this is looking at the individual contribution for each of your predictors. And so we're going to look for whether this is significantly different from 0. Or sorry, is 0.05 or less, which indicates whether the slope is significantly different from 0. So yeah, it's still using that same 0.05 alpha criterion. Again, you can always choose a different cutoff point. You can choose a 0.01 if you want, but most of the time we use a 0.05 to determine statistical significance. Yeah. So you can look at everything. When you have these kinds of tables, it's not good. You never want to look at just one number and then move on. You really should be looking at the whole thing, and the whole table with all the data together tells you the story. So we want to look at, yes, the R. The R tells you the correlation coefficient between the predictor or predictors and the outcome. R squared is simply literally R that has been squared, and this is the proportion of variance explained by your predictors. That's important. You can look at the change in the R squared. So is there a significant improvement in the prediction accuracy or the explanatory value? Right? Here we can see that no, there's not. You can also look at the F change. Is there a significant improvement in the variance explained relative to the variance unexplained? So all of these are important to look at, and they just tell you how the model changes when you're adding variables to it. Great. Yeah, good. Other questions? Okay, so mediation is how we can assess whether a third variable is part of the causal chain. We need to first check that the presumed mediator is in fact a mediator by establishing that there is in fact a significant path A and path B, right? So yes, our X predictor variable does predict the mediator. The mediator does predict the outcome variable. Great. And then, what is the improvement in the prediction accuracy of our model when we add our predictor of interest after controlling for our mediator? Does the predictor of interest have a significant relationship to the outcome variable? Does the slope differ significantly from 0 when we've accounted for the variance that can be explained by the mediator? That's that C prime pathway. So it's the relationship between our predictor and the outcome variable that is on top of or independent of the variance that can be explained by the mediator. Okay? Now, to establish that mediation has occurred, we look at those things. We also might want to look, Barron and Kinney really are just assessing whether or not there is a change in the path C to path C prime. That's kind of, that's one basic way of establishing that mediation has occurred. Does it go from significant path C to non-significant path C prime? That would suggest that there is full mediation. Are they still significant, but C prime is weaker? Okay, that suggests partial mediation. That's how we can establish that mediation has occurred. You can also use the Sobel test, which is testing the significance of path AB. So does that path AB, right, does this, when we look at this combined, is this statistically significant? That's another way of establishing that mediation has occurred. Okay, and yeah, you can always use bootstrap confidence intervals to establish significance. Now, the final thing to note for mediation. A significant XY correlation in the wrong direction. Sometimes you get that it is positive, whereas you think that it should be negative or something like that. If you get a situation where the path C is in the wrong direction from what you think it is, it could be because there are additional mediations links that are in the negative direction, because you guys know that a negative times a positive gives you a negative, right? So if you get something that's in the wrong direction, it just suggests that maybe there are additional mediators that are not being explained that can account for why the total effect is in the direction that might be opposite from what you think it should be. And finally, this is a bit counterintuitive. Sometimes there is a non-significant total effect, but still significant mediation. Now, this is weird. How can we have mediation between X and Y if X and Y aren't significantly related in the first place? This comes down to a power issue. It's not a great way. There's no easy way of explaining this other than that sometimes you get a non-significant correlation between X and Y, your predictor and the outcome variable. So that zero order correlation sometimes is not significant. That does not mean mediation cannot still occur, because the ability to detect a correlation between X and Y is a lot weaker than the ability to detect the mediator relationship. And again, I'm not going to get into an explanation for why, because it's very complicated, but just note that sometimes there are power issues, and so even if you get a non-significant total effect, you should still carry on to assess for mediation. Okay. Quick summary. According to Barron and Kinney, to show mediation, the predictor must predict the mediator must predict the outcome variable, and then we can assess the relation between the predictor and the outcome variable once you have control for the mediator. So those are those 4 steps using that Barron and Kinney method. Another way to assess for mediation is to use the Sobel method to look for statistical significance of those path A and B that have been combined. A total or direct effect of X on Y in the wrong direction could suggest additional mediators that are not being accounted for in your model. And then finally, sometimes you might get a non-significant C pathway, so a non-significant XY association, but that does not necessarily mean mediation cannot still be occurring. Okay, we are going to move on because we have one more topic that I want to quickly cover, and this is moderation. And moderation is going to be really important for the subsequent weeks when we start talking about the ANOVA. Now, moderation, you guys remember from a couple of weeks ago, is when you have a third variable that influences the relationship between X and Y. In mediation, that third variable is part of the causal chain. Variable X causes a change in variable Y because of variable M, right? Because the mediator is being changed by your predictor. When we talk about moderation, we're saying that the association between your predictor and the outcome variable is influenced by the moderator, but the moderator is not causing a direct change in the outcome variable. It's simply influencing the association or that relationship between the predictor and the outcome variable. So, for example, maybe we're looking at the ability to find joy in your free time and your overall life satisfaction, and maybe we see that this is moderated by sex, that females are just generally able to find more joy, they get more bang for the buck in terms of finding joy in their free time. That even at the lower ends, if people have low ends levels of finding joy, then you tend to see females having higher life satisfaction, and that for every improvement in finding joy, we see a bigger improvement in life satisfaction for women versus men. So the relationship between finding joy in your free time and life satisfaction is influenced or moderated by your sex. This is one example, right? So what we're saying is that the relationship between finding joy and your free time and life satisfaction differs as a function of whether or not you are male or female. Maybe we're looking at the relationship between hours studied and grades, and we see that this is moderated by the interest in statistics, such that people who have high interest, it doesn't really matter how many hours they study, they tend to do really well. But if you've got low interest in statistics, then there is a big relationship between hours studied and your grades. People who have a low interest in statistics will have lower grades if they don't study much, but higher grades if they study more. If you have a lot of interest in statistics, then maybe you just, this just helps you pay attention more or whatever it might be. So it doesn't matter really how many hours you studied, you tend to do well if you like statistics. This is another example. So the relationship between hours studied and grades differs as a function of whether or not you like statistics or you don't like statistics. So your interest in statistics moderates the relationship between grades and hours studied. Maybe we see that there is what we call a crossover interaction. So there is some research to show that if we delay the feedback, that the perceived difficulty of a task will influence how the delay of feedback is related to grades. So if you do immediate feedback and it is a difficult task, so immediate feedback tends to result in poorer grades, versus delayed feedback, this tends to improve grades. But for easy tasks, we see the opposite behavior. Easy tasks, immediate feedback leads to better grades, whereas delayed feedback leads to poorer grades. So again, the relationship between the immediacy or the delay of feedback and your grades differs as a function of whether the task is easy or hard. These are all examples of moderation, where a third variable changes how your predictor is related to the outcome variable. Any questions? So in moderation, the effect of one variable on the dv changes as a function of the level of another variable. The effect of hours studied on grades changes as a function of whether you like statistics or you don't like statistics. The effect of finding joy in your free time on overall well-being changes as a function of whether you are a male or female. The effect of delay of feedback on grades changes as a function of whether the task is easy or hard. So these are all examples of moderation, right? Where the effect of one variable on another changes as a function of your third variable, your moderator variable. Moderators can change the strength of the relationship, like we saw with the finding joy in free time and well-being, where this was a stronger correlation with females versus males. It can change the direction of the relationship, like we saw with delay of feedback on grades as a function of whether the task is easy or hard. It's not causing the relationship, but it is influencing the relationship. Now, when it comes to mediation versus moderation, again, mediation is part of the causal chain of events. X causes a change in Y because it causes a change in the mediator, which therefore causes a change in Y. When we talk about moderation, X results in a change in Y, but this is influenced by the score of your moderator. Now, you might have a question. Is my variable a mediator or a moderator? It's a good question. This is one that you need to establish before you begin your analyses. Because your analysis is not going to tell you whether your variable is a mediator or a moderator. It's going to spit out some numbers that may or may not make sense. But whether your variable is a mediator or a moderator comes back to that literature review that you should have done in the first place. So you should have looked at the theories for how these variables are related together, and that will guide you in thinking about how they are related. I have many times read theses from students where they analyze a variable as a mediator or they analyze it as a moderator, but they're not explaining. And they're actually, in fact, describing it. If they're using it as a mediator, they're in fact describing it as a moderator or vice versa. And when I ask them, why did you think that this is a moderator? Or why did you think that this is a mediator and not a moderator? They don't have a good explanation. You need to be able to justify, if you're using this variable as a mediator, if you think it's part of the causal chain, why? What is the research to support why you think this variable is part of the causal chain of events and not just a moderator? Because the SPSS output isn't going to tell you, oops, you made a mistake, you're analyzing this as a mediator, but you should have been doing it as a moderator. It's not going to tell you that. That's where you, as the researcher, come in and use your own judgment. Okay? So make sure you've established these things before you do the analysis. Okay, again, we don't have enough time, but I want you guys to be thinking about some examples of moderation and think about what are some examples of mediation. How are these going to be different from moderation? So I want you guys to think of this on your own. When you do this statistically, each of your variables, your predictor and your moderator, are separate predictors, and then you have an interaction effect. So this is hours studied, over here, hours studied and interest. So this is the moderation, or what we call the interaction effect, and that gets put into the model as well. So we have a regression model that includes a coefficient for our predictor, a coefficient for our presumed moderator, and a coefficient for the interaction effect. And this is going to allow us to assess whether or not our presumed moderator is influencing the relationship between X and Y. Now, one thing to note here is that the moderator is called a moderator only because I've decided to call it a moderator. Statistically, it is no different from another standard predictor. So your moderator is something that theoretically we think is a moderator, but when we put it into the analysis, it is statistically no different from variable X. Now we're going to come back to talking about moderation and these interaction effects in a few weeks when we start looking at factorial ANOVAs. Because in a factorial ANOVA, we are looking at multiple predictor variables. And we want to see how they interact, how they moderate each other. So this is going to come back to haunt you in a few weeks when we go through the ANOVA. So when the interaction term is added to the equation, your coefficients are going to represent each of your predictors plus the interaction effect between those predictors. So all of those are going to get added to your regression model. Now, we can also do this using hierarchical regression analysis, where you add in the moderator, your predictor and your moderator into step 1 and the interaction effect into step 2. I'm not going to show you how to do this in SPSS because actually there's a better way that uses a plugin. So if you go on to do moderation for your own research, you will find a much more efficient way of doing it. So I'm not going to show you the stepwise version here, but just note that it's basically doing a hierarchical regression analysis. So hierarchical regression is used to assess both mediation and moderation. You do this using mean centering, which means you subtract the mean from each variable. And this is because we want to look at the effect of variable m while holding the other variable at its mean. So in your textbook, they describe this, where when we look at the effect of each variable, we're holding the other variables constant. And when we look at the interaction effect, what we're saying is when the other variable is 0, what is the effect of variable m? Sometimes that just doesn't theoretically make sense. If age is equal to 0, what is the effect of of having a happiness score of 20? If age is 0, you're dead. You're not with us anymore. So it doesn't really make sense. So usually for theoretical purposes and for interpretation purposes, we'll do a mean centering where we just subtract the mean from each of our variables. Okay. So quickly, in moderation refers to situations in which the effect of one variable on the dependent variable is related to the level of another variable. And this can be modeled using a combination of regression equations that represent the main effects and the interaction effects. So we would use hierarchical regression. You put in the two predictors into step 1, the interaction effect into step 2. Do center the variables to make sense of the main effects, and then interpret the regression output exactly as you would earlier. You would get the multiple steps, just as you did earlier. If you see in step 2 a significant interaction effect, if the slope for that interaction effect is significantly different from 0, it suggests that there is a significant moderation effect. Okay. That's it. Any questions about moderation? Okay. 5-point summary. Construct the linear model by adding predictors simultaneously or sequentially. Hierarchical models are used to test a specific theory about how predictors are related to the outcome variable, and we can use hierarchical modeling to assess for mediation and moderation. Stepwise models use the statistical relationship between your predictors and the outcome variable to determine the order in which the variables are added or removed. So mediation is when the third variable is part of the causal chain of events, or presumably it's part of the causal chain of events. And we can assess whether mediation occurs by establishing that there is a significant association between our predictor and the mediator and the outcome variable, and whether the relationship between our predictor and the outcome variable is significant once we control for the variance explained by the mediator. We can establish whether moderation occurs, which is when the effect of one variable on the outcome variable changes as a function of your presumed moderator. We can assess whether that occurs by looking at the interaction effect. So simply looking at how the predictor and the moderator relate to each other. we would put those into your regression equation using, again, that hierarchical regression method. You put in each of your main effects. So the predictor and the moderator go into step 1. The interaction goes into step 2. And then we can just assess whether moderation has occurred or not occurred by assessing whether the interaction is significant. Okay. If you are confused, read about this in your textbook that has a much more fuller explanation about some things. There's always a discussion forum, and you can always email me for help. We'll quickly go through the final quiz yourselves. So go ahead and log into the WooClap. Okay, so sequential models yield more valid results than simultaneous models, even if the same predictors are inserted. That is false. They don't necessarily yield more valid. It really depends on what you're doing and how you're using these, right? So it's not by default that they will always be more valid. It really just depends on what you're trying to do with them. All right, next question. Which kind of model is constructed based on the researcher's theory? Okay, correct answer, yes, great. Most people said the hierarchical model. This is the theory-driven model. Very good. So you, the researcher, decide the order to add the variables. You generally add control variables into the first step, and then you add variables of interest into subsequent steps. Very good. Next question. What is the difference between a mediator and a moderator? Okay, correct answer, yes. Most of you guys got that one correct as well. Mediators are part of that causal chain of events. A moderator is a variable that influences the relationship between X and Y, but it's not causing it. Very good. These are very similar words, so make sure you guys are able to tell them apart. Good. Next question. What does it mean if C is significant but C prime is not significant? Okay, correct answer. Mediation is complete. Again, C is the total effect. It's the zero-order correlation between your predictor and the outcome variable. C prime is the mediated effect. So if C is significant but C prime is not, this suggests that you have significant and complete mediation, that the relationship or the explanatory value between predictor X and outcome variable Y can be explained entirely by X's effect on the mediator and the mediator's effect on the outcome variable. And when we take that relationship into account, when we hold that constant, there is a non-significant amount of variance left over for the predictor to explain. Good. All right. What is the indirect effect in mediation? Okay, yep, most everyone got this one. It's the A-B pathway. So the mediated effect or the indirect effect is the relationship between your predictor and the mediator, and the relationship between the mediator and the outcome variable. So that's the pathways A and B. What is another word for moderation effect? Okay, yep, the correct answer here is interaction effect. This is a term that you're going to hear a lot in the coming weeks, so just keep in mind that interaction is basically the same thing as moderation. Last question here. Which of the following best describes a moderation effect? All right, correct answer here is D. So again, moderation is when the relationship between your predictor and the outcome variable changes as a function of your moderator. So here, the relationship between temperature and aggression, right? We have men having a stronger relationship between temperature and aggression compared to women. So this is an interaction. Whether you are a man or a woman influences how the temperature relates to how aggressive you feel. Now, this one, number A, is not moderation because it's the same regardless of whether you're a man or a woman. So this is a main effect. It doesn't matter what your sex is. There is a certain relationship between temperature and aggression. Men are more aggressive than women. Separately, people get more aggressive in higher temperatures than in low temperatures. This describes two separate, what we call main effects. Men have more aggression than women. That's one main effect. Independent of that, higher temperatures lead to more aggression. So those are two separate things, and these are not. This is not saying that the relationship between temperature and aggression changes as a function of sex, which is what moderation is. And then similarly, the third one is describing a main effect again. So remember that moderation is when the effect of the IV on the DV changes based on the moderator. Okay, that's it for today. I think that's it for today. Okay, guys, enjoy your rest week. Also, there is going to be a mid-semester survey that's helpful for me to know how you guys are doing and if we need to change anything for the rest of the semester. So do please make sure to look on Canvas for that. Bye.